Hello and welcome to this APL quest episode. See APL Wiki for details. Today's quest is the last problem from the 2013 round of the APL problem solving competition. We are simply given a set of linear equations and the values that those equations add up to, and then we are to find a solution for the variables. Let's start by creating this equation system. So we'll have a simple example of just three equations with three variables. So this is saying 4x plus 1y plus z and 2 of each, and then 6x plus 3y plus z. And they should add up to a result, which is 264. So 4x plus 1y plus 3z equals 2, and 2x plus 2y plus 2z equals 6, and so on. And a solution to that is if x is -1 and y is 3 and z is 1. And we can check this. So we have the matrix, and then we'll multiply each row by these values, and then we can sum them up, and we can see that we got these results. So indeed, 4 times x, where x is -1, plus 1 times y, where y is 3, and plus 3 times z, where z is 1, gives 2, just like we're supposed to have it. We can write this a little bit neater as a inner product. And so the problem here is that we don't know this result, -1, 3, 1. We want to compute it. What we do know are these values 2, 6, and 4. So in other words, we want to find a v and such that m plus dot times this value gives 2, 6. That was right. It gives 264. Yeah. So this matches an R. And luckily, we can actually write this up. So we can say we want to apply this -1 time to get this value. This is a power -1, applying a function in reverse, applying it -1 times, really asks this question: what argument, in this case right argument, we're giving it a left argument over here, what right argument can we give to m plus dot times such that we get R? And that solves the problem. Now, in the problem specification, R is the left argument and m is the right argument. So we can type up our solution as plus dot times power operator -1 commute. Just swap the two arguments like that, and then the matrix goes on the right and the vector goes on the left, and that's a proper solution. However, and we can check this, of course. We can check that v matches this. Oops. However, this matrix multiplication in reverse, it's actually the same as multiplying by the inverse. So we can and the inverse of a matrix we have in APL as a primitive. We can then state this instead as multiplying by the inverse. Yeah, the inverse like that. And then we can glue them together. So it's the same thing as the explicit formula like this. But for now, we'll have it in a proper assignable function like this. So this is multiplication by the inverse. And the dyadic form of this character, which is often nicknamed domino, it looks like a 1-1 domino, is actually exactly that. So the entire solution can just be that. In other words, this problem has a one-character solution in APL. Now, that's of course lots of fun, but it would be nice to see how we could really solve this without APL just doing all the work for us. And there are a couple of ways to do this. There's a really clever way to do it called the Hotelling-Buddhic scheme, if I pronounce that correctly. And it states that we can do an iterative approach to approximate better and better the correct solution to an inverse of a matrix. And as we had before, if it's easier to do matrix multiplication. So if you have the inverse, then the problem is basically solved. And it states like this, that we're going to iterate with this result where every iteration depends on the previous value, and we are going to, the formula looks like this. I'm not going to go into exactly why this works, but this is what they state. You can see, look up their paper. So this is what they say, that the next iteration is the previous iteration, a matrix, multiplied by 2 times the identity matrix minus the grand matrix, that the original matrix that has been multiplied by the previous iteration. And we can rearrange this formula a little bit. We can take this vi here and sort of say multiply into the parentheses. So that gives us 2vi, because the vi multiplied by the identity matrix is just vi, of course, minus, and then vi times a, which is the original matrix, times vi again. And we can then state this in APL. The way we would write that is we can write 2vi, or we can, so 2 times vi minus vi plus dot times, which is the matrix multiplication, and a plus dot times vi. And we can break this, avoid the parentheses, simply by having 2 vi's here instead. It will be the same thing as multiplying it by 2. And now we can make this a function of the original matrix on one side. So we have a, and then we make a function, and we have the previous iteration as the right argument. So we'll do it as a test function. So we start from the right here, build it up. First we want the matrix multiplication of them, plus dot times. And then we want to multiply by vi again. So vi is the right argument, plus dot times that. And then we want to subtract this from vi, that's the right argument, minus that. And then we add another one of the right arguments. We can write it up like this. So here's a tacit way to compute this. And this is one iteration of it. However, we actually want to keep doing this until it becomes stable. And the way we would then write that, we could take it as a function where the right argument, function of the original matrix here called A, so that becomes fed into our inner function as a left argument, and then we keep iterating with the power operator until 2 consecutive iterations are the same. And so then we just need to apply this whole thing on our initial guess, and that's the next problem. So the problem is it's kind of hard to find an initial guess which will work out for us. But recently, someone named Soleimani came up with a surefire way to determine an initial guess. And what he stated was that the transpose of the array divided by the trace of the matrix times its transpose is a good starting guess that will always come out. And again, see his paper if you want the details of how exactly that works out. So we again, the trace of the matrix times its transpose, and then we divide the transpose by that. So first we do the trace of the matrix times its transpose. We can have this matrix M, and we can transpose it. And then we can do a matrix multiplication with itself. And then we want the trace. The trace is the sum of the major diagonal from top left to bottom right, and that we can do as a 1-1 transpose. That's the trace of that. And then we sum that up. So for our matrix M here, that magic value that we want to divide by is 84, and then we would go ahead and divide the transpose of M by 84, and that would be a good starting value. Now, we could use this, but it can actually be simplified a little bit, and for that we need to observe some characteristics of doing exactly this, the trace of the matrix multiplied by its transpose. So what we're going to do is we'll start with a matrix that is easy to recognize where the bits and pieces are going. And instead of doing an actual multiplication with itself, we are going to take and model the plus and the times as functions that are just saying what they would do rather than actually doing them. Oops, there should be a times over here. Okay, so this will show us. It will create little boxes showing us what's going on, and we need to multiply it with itself with the right argument to the matrix multiplication being transposed. So here we can see all the results that we're getting, but we're only interested in the diagonal. So we're taking the 1-1 transpose of that, and now we can observe exactly what's going on. Right? And remember, the trace is the sum of these. So really, what would happen is we're going to add all these together, all these little boxes, and notice that is 1-1 multiplied by each other, and 2-2, 3-3, and so on. That means every element of the entire matrix gets multiplied by itself squared, and then we just sum all these squares together, which means we can state this much easier. We can just ravel the matrix, square it, and sum it, or we could of course square it first, ravel it, sum it. Many different ways of doing that. We can also combine this summing and multiplication into an inner product, and that means that if we're going to write in the train, we want this as short as possible, then we can write the ravel plus the times the ravel of the matrix, and that gives us that. And now we just need to take the transpose of the matrix and divide by that. So we can take the transpose, divide by this, and that gives us our starting value, which isn't very interesting to look at. But let's put all of this together. So what let's go up and get it from up here. we had this formula right here, and we stick it in here, and this is then the inverse that we get. We can compare this with the inverse primitive and see we got the exact same value. And now remember how we solved this with V. So we can go in and say V plus dot times this inverse. Oops, sorry. It should be must be like the other way around. What am I doing wrong here? Oh, here we go. R instead. And this is a solution, but we want to glue these two things together to be a single function. So this right part here is the inversion of the matrix, and the left part is the matrix multiplication. So we multiply with the inverse, and that gives us our solution. We can, and remember this is an iterative thing. So inside here is the power match, which just runs over and over again until two consecutive things match each other. And it would actually be neat to see how this would look. We can do that by doing each iteration separately. Now I happen to know that we only need to go through 11 iterations. So for every one of numbers from 1 to 11, we're going to apply it that many times, and then we can see the progression of better and better values for x, y, and z to solve this system until we're done. It becomes stable. So this is a modern computational approach to this. Traditional way that you might have learned in school is the Gauss-Jordan method, and you can find it in the defense workspace. Here is an adapted version of what you found, what you can find there. I'll try to explain it a little bit. What it's doing here is, if you learned in the school, you would have learned that there are these various actions you can take on your matrix together with the result values to slowly build up diagonal matrix, and then you have a solution. When we running it as computer code, then we can't go by a feeling of what's easier. Instead, we just go through all the steps every time. So what we're building up here at the bottom is this is our equation system. These are the final values that we're putting next to it, and then these are the reversed indices, because reduction runs from the right to left. So that's what this comment is trying to say, that this is what we're going to reduce over. So this just eliminate here, eliminate here, eliminate here in this order. And every time we eliminate, we choose, for precision reasons, we choose the row that has the largest magnitude. So this gives us a specific column that we start. So because we're going down diagonal, so first we start the first column, and then we get rid of the first few elements that have already been those columns that have already been taken care of. Of course, with the first one, that means we're dropping 0. Notice that the index origin is 0 up here. And then we look at the magnitudes and choose the largest one, and that's what we call our pivot row. And then we swap things around. So where we're up to in the nth row and the pivot row, we're taking those and just flipping them. There's just 2 of them, so then reverse just swaps the 2 around. And now we've got a matrix that's modified by having these 2 swapped around. And then we want to normalize such that in that corner, or should we say, of the submatrix missing rows and columns, that is on the intersection of the nth column and the nth row. That's why we have alpha semicolon alpha here. We divide that. We divide all the other values there, so that we get a 1. And then finally we have the step of adding or subtracting. And the way it's been done, implemented here, is we are adding, subtracting not just for that single row, but we're doing the entire matrix. So it's built up using masks. Essentially, when we add or subtract 0, then nothing happens, and we're using a mask. That's right here. These are all the indices for all the rows, and then we have a specific row number here, which gets so wherever it's different from, we get zeros, and that means we only get 1 on this single row. Then we pick out from that column there, and create a matrix with all the values that are in this particular row. And then that effectively just has a bunch of zeros, and we subtract the right values in the right place. Once that's done, since we've done a reduction, we have enclosed, so we open that up. And we're not interested in the entire matrix with result values. Rather, we can chop those away. So that's what this is doing. And then, just in case they were all identical, we used a single value. We just reshape it to have the right shape. And that's how the Gauss-Jordan method works. And we can try that. It solves the whole thing immediately, like this, in exactly the same way. And then I happened to look up in an the old paper on APL 360, and it was actually interesting. It brought us an example of code, this function, which is inversion of a matrix, but implemented in old style APL. I'm not going to go through and explain this. You can do it on your own. It's really very much, it is the Gauss-Jordan method. It's very much the same, but in a old style, without using any of the new operators. I've altered one slight thing. You can see a capital A in there. That was an original function in APL 360. It had some functions called alpha and omega, which were prefix and suffix vectors. So alpha, or which I've changed to an A here because alpha is now meaning something else, and you can define it like this. In our case here, where it's so the left argument is the length of the vector, and the right argument is the number of leading ones in that Boolean vector. In our case, it could just be a take, but I suppose overtake, meaning you can take more elements than there are in an array, wasn't supported yet at that time. So you can actually replace these A's just with an up arrow. And this gives us our inverted matrix, as we can see from before. Same thing as the primitive. And that means that we can do the same thing here with multiplying the result of the inversion with our desired result values, and that gives us our values for x, y, and z in the very oldest of fashions. So this concludes the first year of APL problem solving competitions, and we're now going to continue next time with the problems from 2014. Thank you for watching.